Hi everyone, Mrs. Besega here, and today we're working on the Unit 1 review for 5480 physics class. So what you should be doing with this is first, you should complete the review on GoFormative, the one that looks just like this. You should complete this entire review and then hit submit. Once you hit submit, you'll be able to see your answers and how you did on specific questions. Then, watch this video for the questions that you struggled with. I don't expect you to watch this entire video, just the ones that you need to relearn or rethink. So, getting started. On the right is the review as it looks like on your iPad. On the left is me going to be showing my work as I go and helping to explain some of the concepts as we reach them. One thing you might notice is that I draw a lot of free body diagrams and graphs and pictures to help explain things. You should feel free, even though this test is on GoFormative, to use paper and pencil and other ways of taking notes or writing your workout as you go through the test to help you understand these better. So let's get started. For number 1, a buggy pulls horizontally on a book. So we're picturing like a car pulling to the right, like a tumble buggy. We'll call that a tension. And the book is not moving. I know in the y direction that means that there must be a normal and gravity force that cancel. If the book is not moving, it's in equilibrium. In the x direction, that means there must be a friction force. The friction force will balance the tension, so I'm going to label these forces with a little dash to indicate these forces are equal magnitude. All of that is from this little special phrase, is not moving. That indicates static equilibrium. So which of the following statements is true based on the free body diagram we just did? I see that tension must be equal to the force of friction, not the weight. Notice that the weight and tension are not equal to each other because they're not in the same direction. So tension is equal to the force of friction. For number 2, an astronaut is spacesuit training on the Earth. On Earth, the astronaut has mass because they're made of matter. That mass is proportional to the amount of matter they have, and all mass and matter have inertia. That is the resistance to changing their motion. Think like a heavy, massive object is difficult to move. Well, when our astronaut goes to the moon, they're going to have the same amount of mass and the same amount of matter, so the same amount of inertia. But what they're not going to have the same amount of is gravitational field and gravitational force. Remember, gravitational field is the distortion of space around massive objects. On Earth, it's 9.8 newtons per kilogram, but on the moon, it's less. It's only 1.6 newtons per kilogram. The field is the distortion of space near the moon or near the Earth. And it's that field that creates the gravitational force. Now, there's 2 synonyms right here. There's gravitational force, force due to gravity, and that can be equated to the weight. Both of these are similar. So more force, more weight means on Earth, the astronaut weighs more. On the moon, the astronaut has less force, less gravitational force, less weight. So the moon would have less gravitational force on the astronaut than the Earth. So I've only selected same mass and same inertia. For number 3, a block is moving to the left with constant velocity. Notice that that keyword is highlighted. There are 2 forces pictured, but there is a missing third force. So let's draw this out. I have 24 newtons to the right, 16 newtons to the left, And in order to be in equilibrium, I need to find the missing force. Now, just to be clear, some people will get tricked up and say 40 newtons left because it says the block is moving to the left. But let's just imagine for a second. If this was a 40 newton force left, this would be unbalanced and my object would be accelerating to the left, not constant velocity. A net force causes mass to accelerate. So if you want it to keep going on the same speed, you can't have a force to speed it up or a force to slow it down. You have to let it be an object in motion, staying in motion. So actually, all this means is the forces that pull right must be equal to the sum of the forces that pull left. So subtracting 16 to the other side, that means F3 should be 8 newtons. To get the direction, notice that 8 newtons pointed to the left. For number 4, I'm going to build on this Earth-Moon model. On Earth and the Moon, they have the same mass and same inertia. If I bring that same astronaut to Jupiter, it's still going to have the same mass and the same inertia because that astronaut should have the same amount of matter. We're not like taking off one of their arms. So I'm going to sort mass and inertia over to the is equal category. But Jupiter is not like the Moon. Comparatively, Jupiter would take the same astronaut with their same mass and same inertia, but now gives them even the most field. Now the field is 25 newtons per kilogram. Don't worry about this meters per second squared unit. We will deal with that when we get to it. On Jupiter, having more field than Earth must mean it has even more weight than on Earth. Having more force due to gravity and more weight than Earth means that I would take both of these, force due to gravity and weight, and drag them into the 2.5 category. So side by side, they have different fields, which creates different force and different weight, but not different mass or inertia. For number 5, you push on a refrigerator resting on a garage floor with an applied force to the right, but the refrigerator does not move. That's a key word. I can automatically cross out the second 2 choices because I know it's in equilibrium. So this is in static equilibrium, so it's going to be one of those 2 choices. Let's draw this out. The weight of the refrigerator pulls down. The normal force pulls up. I'm going to put labels on each. I'm going to put my applied force to the right. And there must be friction acting left. There's not a string pulling this refrigerator backward. It's just its own friction with the floor. So in this case, if this is going to be in equilibrium, the forces that pull up balance down, the forces that pull right balance left. So friction is balanced by the applied force, and this is in static equilibrium. For number 6, these were the demos I did in class, where I have an object made of mass that stays in place because there's a minimal net force acting on it. You can picture this one like a table with a cup on it. The cup is made of mass. It's an object made of matter, has mass, and has inertia. Inertia prevents this object from accelerating. So when we pull this to the left really quickly, if you have a minimal friction force, the inertia wants the object to stay in its initial position, or its initial velocity. Inertia prevents acceleration. So since this object is currently at rest, it's going to stay at rest because inertia prevents acceleration. Notice that the other four choices are all examples of forces. Forces cause mass to accelerate. If weight, normal applied, or friction were unbalanced in their favor, in their direction, that force would cause it to accelerate. So remember, inertia is not a force because forces cause acceleration when they're unbalanced acting on an object. But inertia prevents acceleration. Those are not the same thing. So inertia is what wants to keep an object at rest at rest. For number 7, the key difference between velocity and speed is that velocity is a vector and speed is a scalar. To remember the difference between vectors and scalars, remember Vector the superhero or the supervillain. A vector is a quantity with magnitude and direction. I like to remember that velocity is a vector because V for velocity, V for vector. This direction means that velocity can be negative if you're traveling backwards. Whereas speed is a scalar. Since it's a scalar and doesn't include direction, it can't be negative. A scalar can be positive only. And speed is a scalar. I remember that because S for speed, S for scalar. So the key difference between velocity and speed is that velocity includes direction. Actually, this hack will help us with number 8. Speed is positive only, so I can go drag this over here. Excellent. Now let's deal with the rest of them. We'll come back to speed versus velocity in a little bit. In this picture, I can see that the position is always a positive number. So please note that even though this line is going down, at any given point, the position is positive. So at 1 second, the position is positive 90. At 5 seconds, the position is positive 50. So all of those positions are positive numbers. What about the velocity, though? The velocity is the change in position over time. Or you can write it as velocity is displacement over time. It's telling how fast you are traveling and in which direction. So let's check our position versus time graph here. And since this is a straight line, I can pick any points along this line to do this math, but I'm going to pick the easiest ones to work with. The displacement in my graph is how much my object has traveled, but taking into account the negative signs. This object travels 100 meters backward. Notice that the difference in the y direction, it goes from 100 to 0. It goes 100 meters back. And it does so in an elapsed time of 10 seconds. So first I'm writing down the equation for velocity. Then I would write that displacement is negative 100. The time is 10 seconds. So the velocity is negative 10 meters per second. I can tell from the graph that this velocity is negative because this downward slope means it's traveling backward. That constant slope tells me something else too. It tells me it is not accelerating. Remember that having a curved graph indicates acceleration as positive or negative. Since this graph is a straight line, this acceleration must be 0. So I'm going to drag acceleration to 0, velocity to negative. For number 9, I've calculated the velocity during the 10-second time. drew this graph so I can do more work for number 18 and show you what's up with this. We have displacement, velocity, distance, and speed, and we want this for the first 14 seconds of motion. So first off, I'm going to ignore this part right here. Pretend it's not there at all. Now, let's deal with the scalars first. So remember, scalars are quantities that have magnitude but not direction. They have positive only. Speed is a scalar and distance is a scalar. So if I can calculate the distance, I can calculate the speed. So let's do that first. So in section A, this object walks 50 meters forward in position in 5 seconds. So I'm going to draw this out. In section B, they walk from 50 meters to 70 meters. So in section B, they walk another 20 meters forward in 4 seconds. Finally, they walk from 70 to 20. They walk another 50 meters backward in 5 seconds. So when we go calculate distance, we're going to add up all the lengths that they walked. So that's 50 plus 20 plus 50 equals 120 meters. Well, they did all of that distance in 14 seconds total. Speed is distance over time, so that would be 120 meters over 14 seconds, and that would give me 8.6 meters per second. But now let's deal with the vector. Velocity is a vector because displacement is a vector. Velocity is displacement over time. So if I can calculate the displacement of this object, I can calculate the velocity. To calculate displacement, I'm going to do the same like drawing logic of drawing the types of motion like I did for distance, except anytime it travels backward, those would count as negative directions. So let's see what this looks like. In section A, they walk 50 meters forward. In section B, they walk another 20 meters forward. Notice this time I'm putting signs on here. It reminds me that next time for C, they walk negative 50 meters backward. So when I calculate displacement, I'm doing the same addition that I did before. It would be 50 plus 20 minus 50. Now that it's displacement, objects that are moving backwards have negative directions, making the displacement in this case 20 meters forward. So put a little positive sign there, forward. Finally, the velocity then. Velocity is displacement over time. So I would put displacement is 20 in 14 seconds. That makes the velocity 1.4 meters per second and positive because it's moving forward overall. So now I just match them up. Distance was 120. Speed was 8.6. Displacement was 20. And that leaves velocity as 1.4. For number 19, there are 2 cars. This is a dot diagram or a motion map. And because motion B starts close and gets farther and farther apart, car B must be accelerating. Car A is traveling at constant velocity, as evidenced by these equally spaced dots. Constant velocity is dynamic equilibrium, so the net force is 0 on A. If you had tried to calculate something here, you'd notice there's no good equation for net force you could use. We knew a distance, maybe a time, right? But none of those things were in newtons. 0 was the only logical answer. So now, for number 21, let's say I have object A as being this nice constant velocity motion. That corresponds to a linear graph with a positive slope. Now let's add other cars. For this, I want to use the line tool. To get to the line tool, click this button here and select line instead of scribble. Car C has half the speed as A, so it should travel half of the distance in the same amount of time. So that's my car C. Next, car D has the same speed as A, but starts ahead of A. So I'm trying to draw a line that's parallel to A to indicate the same speed, but starting from a greater position, higher on the y-axis. Finally, a car traveling in the opposite direction as A would have a negative slope. I'm going to label this E. So we've drawn all our graphs. For number 22, we have 2 painters and 2 tensions and a rope. We know the painters each have a mass of 51 kilograms, and you're asked to calculate the weight. Whether you're calculating mass or weight, you're still going to need to be writing out the same equation. It's just in the mass case, you're given the weight in newtons to find the kilograms. And in the weight case, you're given the mass in kilograms and asked to find the newtons. In this case, mass in kilograms was 51 kilograms. So I'm putting in 51, that's mass in kilograms. G is 9.8. And I'm solving for Fg, the weight. Multiplying these two together gives a weight of 500 newtons. So sometimes people ask like, oh, do I need to divide or multiply? And my response to that is write out the equation and do what you have to do to find the missing variable. If the variable is mass, notice you had to divide by 9.8 to get m by itself. If you're trying to find weight, notice you had to multiply to find Fg. I don't want you to ever memorize it, but rather substitute and then solve how you would in algebra. So for calculate the weight of the painter in kilograms, I'm going to show my work with a picture. You get 1 point for the equation, 1 point for the substitution, 1 point for the answer. So if you just put this with no work shown, you wouldn't get full credit. Now let's draw a free body diagram. In this case, I need to use the line feature, and I want to draw as proportionally as I can. In this case, there are 3 weights pulling down, 2 painters at 500 newtons each, and one plank of wood. If you're typing in here, when you press the type button, you can change the size of your type by selecting different line thicknesses. So I've moved it to medium, so this is a reasonable size. Each painter weighs 500 newtons. The plank is 100 newtons. Of the forces that pull upward, there are 2 tensions upward, but we only know one of their values. So I'm going to call them T1 and T2. T1, we know one of the tensions is 800. And if I don't know the value, I still need to put it in the free body diagram, but I'm going to leave a question mark next to its value. So to get full points on a free body diagram, draw all of the forces, label both their type and the number of newtons if you know it. This makes my work for the next part much easier, because if I keep this picture in front of me, then I can write an equilibrium equation. Since the forces that pull up have to equal the forces that pull down, that means T2 plus 800, both of those tensions pull up, balancing the two weights from the painters that pull down, plus the 100 newtons from the plank. And I can solve for T2. So this would be 1,100 on the right, subtracting 800 to both sides, means that T2 is 300 newtons. And that direction is up. I know that T2 has to be up because otherwise it won't be an equilibrium. Adding my work for number 24, my answer is 300 newtons. So Catherine needs to graph the motion of a car that has 3 points. In section A, the car stays at rest for 5 seconds and at an initial position of 8 meters in front of the origin. In section B, the car travels backwards 10 meters in 10 seconds. And finally, in C, the car travels forward 15 meters in 10 seconds. When I'm looking at this, the screen's very small, so I'm going to hit the zoom in button, and I'm going to draw more clearly here. So I've zoomed in, and in section A, the car stays at rest for 5 seconds. It starts at 8 meters in front of the origin, so I'm going up to 8 and drawing a line that stays for 5 seconds. Next, I'm going to have section B. It travels backwards 10 meters from this position in the next 10 seconds. So 10 meters back from 8 means a position of -2. And it does so in 10 additional seconds, so out to here. I need to connect these with straight lines. So that's section A, B, and finally, section C. The car travels 15 meters forward from this position in 10 seconds. So that would bring me to, in section C, the car travels 12 meters forward in 10 seconds. So going 12 forward from -2 would bring me to +10. And it does so in the next 10 seconds. So by 25 seconds, I'm at a position of +10. So calculate the velocity in section B. In section B, this object went 10 meters backward in 10 seconds. So I can do this just based on the word problems. Velocity is displacement over time. 10 meters back in 10 seconds of time is -1 meters per second. Note that the speed would be positive, because speed's always positive. Think like it's the absolute value of the velocity in a segment, right? But the velocity is negative. At t equals 16, the car is located in a negative position. See how it's like below the origin at that point? All that means is your object is behind the origin. So if you imagine a number line, then your car's just over here. And that's totally fine. You can have a negative position. It just means you're behind wherever it is you started measuring from. Last two, Newton's first law. I did this demo in class, right? So in this case, the apple is an object in constant velocity motion, so it wants to stay in motion. Yes, the table exerts an external force, but the table doesn't touch the apple, so it can't be C. The knife is not at rest during this whole video, so it's not trying to stay at rest. The apple is the object in motion staying in motion. Now, if friction weren't there, the apple would continue to move in a straight line down with a constant speed. Because if the knife-apple interaction were frictionless, that object in motion would want to stay in motion. Frictionless means that there's no force that's going to slow down the apple. For number 30 then, without friction, this would be an object in motion, would be dynamic equilibrium, so the net force would be 0. Now that I've hit submit, it will go and tell me all of my answers. So, hope you did well, and if not, go back and watch this video, and we'll figure it out. Best of luck!